All right, good morning, everyone. Our group will be presenting our project, Toxic Common Classification. Next slide. With the ongoing pandemic, so much of our communication has been moved to online platforms. Our goal as a team is to train a model to identify and classify any possible harmful comments so that these platforms can be kept safe and productive. Next slide.
For our data, we got it from the Toxic Common Classification Challenge on Kaggle. It contains comments from Wikipedia editors, and those comments are labeled in 6 classes, which are toxic, severe toxic, obscene, threat, insult, and identity hate. For example, if a comment is labeled as 100100, it is a toxic and threat comment. However, we had to manually relabel some of them due to label inaccuracies. Next. When we examine the data, we can see that there are over 150,000 comments, and the mean for all the label classes are really small. Since good comments are labeled as 0, this indicates that most comments are good, as seen at the bottom. We also check for any null comments just in case. Next. Also, the data is incredibly messy. We used regex to remove any line breaks, contractions, or slangs. You can see that for the same set of comments, it's a lot more organized after cleaning. Next. We realized that some classes have very few comments, such as threat with less than 500. To get our model to converge better with more comment variations, we decided to use a Python library to generate augmented comments in those classes. And you can see some examples of augmented sentences on the right. Next. The data sets we created in the processing step belong to 2 major categories. The first is a multi-class dataset with the comments split into training, valid, test, and overfit. However, it's very difficult to balance all the classes because the comments are labeled as multiple classes. So we created the second dataset on the right, which has 6 binary class sub-datasets, one for each class. And they all have balanced good and bad comments, and then they're split into the 4 files. Next.
So the baseline model we use is the same as assignment 5, where we have glove embedding layers and fully connected layers. Next. And our baseline model is a CNN, LSTM classifiers. So the comments are first vectorized using glove embedding layers, and then we use 2 CNN layers for feature extractions because we realized that a lot of vocabulary, a lot of bad comments share similar vocabularies. Then they are fed to an LSTM and then decoded using a fully connected layer. Next. So because the classes in our data sets are not mutually exclusive, we try 3 different training approaches. Approach 1, we use a multi-class data set and train a classifier with 6 outputs. Approach 2, we use the same multi-class data set but train 6 binary classifiers. And in the third approach, which is also our best approach, we use 6 balanced binary data sets to train 6 binary classifiers. Next. We can see that the model in our best approach actually performs very well with a training accuracy of 98% and testing accuracy of 95%. There's no sign of overfitting, and also the curves are very smooth. Next. So to make sure that our approach is actually the best one, we also compare the results between different approaches and models. And as we can see from the bottom right, our model is actually performing the best. Next.
Here's a web app to demo our results. So for a good comment, it's correctly classified by our model. This is for one of our training examples. It's also correctly classified as toxic and insult. But if I were to import a comment like this, our model isn't able to extract the full meaning of the sentence, and this is an example of a false positive. That form of confusion matrices we really want to minimize because, as you can imagine, it can be really frustrating for users when valid comments are being restricted.
Next slide. So our model achieved a 95.3% accuracy, which is pretty good. How did we get here, and how can we tackle the remaining 4.7%? Next slide. Here's a set of confusion matrices from an earlier iteration that we trained on unbalanced data. Since there were so many more good comments and toxic comments in our set, we had a huge amount of false positives that we eventually mitigated by balancing our training data. Next. We also saw that after implementing data augmentation, our model was finally able to converge on classes that originally had very few training examples. So as an example, we have threat shown here. Next. And here we have a figure showing correlation between input features and targets on the left. Some features such as obscene and insult show a very high correlation. So as the next step, we can look into implementing things like chain classifiers, basically where our classifier will take the outputs of previous classifiers as another input feature. Next. And for our learnings, our primary challenge was working with real-life data. Working with lots of messy data, a lot of thought needs to be put into the processing step. As well, we experienced firsthand the machine learning workflow is really iterative. There's never an optimal answer, and it's important to evaluate the model in the context of our goal, which in our case meant really minimizing false positives. Because at the end of the day, as machine learning engineers, we're working not to deliver just an accuracy curve, but technologies to serve our community. Thank you for listening to our presentation.
Great. 3 seconds left. Very good. Very interesting topic, and you fought through a bunch of interesting issues. The first really key question I have is the separation of the data sets. Let's see, can I find that in here somewhere? You had to augment and balance these data sets. To be clear, for each class, you created a training set, a validation set, and a test set. Is that correct?
Yeah.
So when you show results for a specific class, which would be, got to find it down here somewhere. Where do I see results for a specific class? It's in the here, right?
I think yeah, sure.
So, and what do we got? True. These are correct positives, correct negatives, and then false negatives, false positives. So, there's a lot of false positives here, right? On severe toxic. And this number, the sum of these numbers is the sum of, that's the size of your training set? Sorry, your test set? You had 1350 plus 785 plus
yes.
7.
Yeah, so that's everything in the subclass data set.
No, is that the size of the test set?
So the results from these confusion matrices were validated on our multi-class data set. So this was one of the reasons why our model was giving us like really wrong examples, because we trained it on the multi-class set rather than the binary set. The results of our final confusion matrices results were actually shown in the VER demo. So this was sort of an intermediate step, definitely not our final result.
Okay. So somewhere in the video, you're showing something. Where'd the video go? It's here, right?
Yeah, it's near the end of the video.
Okay. Here. Yep. So this is the size of your test set. This plus this plus this plus this.
Yep.
Yeah.
What was the size of your training set? For say that one.
So I think for our split, we did 80-10-10.
Oh, so you have tens of thousands of these. So you have quite a few.
Oh yeah.
Yeah.
That's cool. That's really interesting. Well, this you can partly blame on me. You didn't have enough time to describe your results, but you should know you can't throw up a slide like this and go, and here you can see, and because no one can see anything when you blast it through this in a second or two. You should never, even though many people do this, you should never put this many graphs on a single slide. Physicists do it all the time. I would like to train computer/software/ML engineers to not fall into that just stupid trap. If there's a thing to say, you show it with one graph and you go, here you can see. So, and now some of this is my fault. There's not enough time to go through all of these. So your job was to have picked the most important thing to say and show it. And so blasting through things is, just don't leave this class. I'm saying that a lot lately. Don't leave this class thinking this is in any way acceptable. And I'm saying this not to criticize you, particularly want everybody to know that this just doesn't work. But I am curious. There's all kinds of data here. And actually what I didn't quite pick up was the difference between, before we can even go there, this approach and this approach. So approach 1 is a multi-class classifier. Approach 2 is what? Tell me what approach 2 is.
Okay, so in in approach 2, the multi-class data set is used to train each of the binary classifiers.
And how do you use a binary class? How do you use a multi-class data set to train?
So multi-class data set, we set the CNN classifier to have 6 outputs. That each of the outputs just predict one class, and then in the binary class, each classifier predicts one class.
And so in the training, are these separately trained?
Yeah, they are separately trained.
There's a separate loss being propagated back through here, each of these things.
Yes.
And you're calling that the multi-class data set. So, and then you did something else. You separate out the data set so that each thing is itself binary, either the thing you're looking for or everything else.
So for example, in the best approach, dataset 1 only has labels of the toxic class, and then the classifier 1 only classifies toxic dataset.
Well, so the label 0 means is all the other classes, is whether any one of the other classes was true. Is that right?
There's just no data set for any of the other classes in the third approach. So just we train one classifier with one.
No. A data set has to have a negative labels. It can't only have positive labels. So right, there's got to be 1s and 0s in this data set.
Yeah.
What's the 0?
Yeah, they are.
So what's the 0?
So 1s are the.
I know what the 1s
zeros are the good. Yeah, zero are just there's no label as toxic for this comment.
Yeah, the good comment.
But could it be? No, you got to be more clear than that. Actually, it could be no non-toxic. I guess none of the classes.
Yeah.
All right. Good. That's the word. Yeah. Good, right. Yeah. Okay. So it's only good versus the specific class. I see. And this worked best, you're saying. That's interesting. That's an interesting exploration. Okay. And then somehow this is the comparison of all those things, right? Except here there isn't just one classifier, right? There are 6 classifiers or 5.
Yeah.
So you're showing 6. What are you actually showing here?
So these are the combined loss and combined accuracy, which is average the loss and accuracy.
Across the training, I see.
Across each class, yes.
Okay, so that's a bit misleading. You wouldn't say it. You would have to say that more clearly. That's the trouble with gluing too many things together at once. Okay. I thought your idea at the end, by the way, of chaining is a good idea, because there's always getting some information from the other classifiers could help this classifier. So I like that. That's a cool idea. Saurav, any comments, questions?
Yeah. So you mentioned in the slide that the data set you downloaded, they were already labeled, but you had to relabel some of them. So what proportion of data set you had to relabel?
So we roughly looked through the data set, and we saw anything that's 2 out of they're labeled very wrong. So I don't know how many we relabeled, but it's just whatever we saw.
Okay. And so in the dataset split slide, you had mentioned train, validation, test, and overfit. So I was wondering, what's overfit?
Yeah. So Professor Rose, in our assignments, he taught us to always have an overfit set so that we can. It's only for debugging. It's not for actually training the model. So it's only to make sure that our model is actually recognizing patterns.
Okay. And I really like the idea, the way you did data augmentation by replacing words by synonyms. So that was pretty cool.
Thanks.
Yeah, that's a well-known way of doing it. You don't have to separate out the overfit data. You can reuse it when you're training. It's not something that needs to be separated, by the way.
Oh yeah, so our overfit data is duplicated from train valid set. It's a subset of training data.
Yeah. Okay, that's great. So normally you don't talk about it as a thing.
Yeah. Okay.
But although overfitting is a key concept to walk away out of this class with, for as you would have noticed on the term test, actually, I asked you. So, Okay, great. Any, sorry, I should have called you Shashank, not Saurav. Anything else, Shashank?
No, that's everything from my side.
Any questions or comments from the class or applause?